Acid-base equilibrium, Henderson-Hasselbalch equation. In this tutorial, we will be going over the factors that influence the pH of a buffer, overview of the Henderson-Hasselbalch equation, two methods, Rice table and the Henderson-Hasselbalch equation. We'll be looking at a worked example of a weak acid conjugate base, another worked example of a weak base conjugate acid, and then finally talking about buffer capacity. Factors that influence the pH of a buffer. Two factors influence the pH of a buffer. The first is the pKa of the acid, and the second is the concentration of the weak acid-weak base pair. The Henderson-Hasselbalch equation is used to describe the relationship between the pH of the buffered solution, the pKa value of the weak acid, and the ratio of the weak acid and its conjugate base. Assumptions. The molarities of the acid and conjugate base, or base and conjugate acid, are relatively equal to their initial concentrations. Acid and base initial concentrations are typically large. Let's talk about how we derive the Henderson-Hasselbalch equation. So we're given the equilibrium expression, Ka is equal to the hydrogen ion concentration times the concentration of the weak base divided by the concentration of the weak acid. What we're going to do next is take the log of both sides of the equation, as you can see right here. The log of two numbers divided together can be solved by taking the log of each number and subtracting the log of the denominator from the log of the numerator. In this case, we only want to isolate the hydrogen ion concentration and leave the ratio of the concentration of the weak base to weak acid. Then we're going to take the log of both sides, where log is replaced by p. The final step to derive this equation is to divide the negative pH and the negative pKa to make the variables positive, which results in pH is equal to pKa plus the log of the weak base divided by the weak acid. The Henderson-Hasselbalch equation is used to provide general information about a reaction. When the conjugate base and the weak acid concentrations are equal, the log term is dropped and pH is equal to pKa, as well as pOH is equal to pKb. When the conjugate base concentration is larger than the acid form, Ha, the log term is positive and pH is greater than pKa. When the conjugate base concentration, A-, is less than the acid form, Ha, the log term is negative and pH is less than pKa. To summarize, adding small amounts of strong acid or strong base to a buffered solution does not significantly change the ratio of weak base to weak acid, and thus does not significantly change the solution of the pH. The change in pH upon addition of strong acid or strong base to a buffered solution is therefore much less than it would be in the absence of a buffer, and we'll see this more when we talk about titration curves. Worked example, buffer containing a weak acid and its conjugate base. Method 1 will use a Rice table. So determine the pH, that's our goal, of a buffered solution that is 0.250 molar HCN and 0.170 molar KCN. Our Ka value is 4.9 times 10 to the negative 10. The chemical equation for the strong electrolyte is KCN dissociates into K plus 1 and Cn minus 1 ions. The chemical equation for the equilibrium system is HCN ionizes to form H plus 1 ions and Cn minus 1 ions. So using our Rice table, initially we have a concentration of HCN of 0.250, no hydrogen ions, and our Cn-1 concentration is coming from the strong electrolyte. Some amount of the HCN will ionize to form some amount of hydrogen ions and Cn-1 ions. Here we are assuming that X is small based on our Ka value. Our next step is to write our equilibrium expression. Then we take the values from the stimulus and plug those in. So our Ka is 4.9 times 10 to the negative 10. We are solving for X, which is our hydrogen ion concentration. The 0.170 is coming from the stimulus, and the 0.250 is the concentration of the weak acid. If we do the calculation and solve for X, X is equal to our hydrogen ion concentration, which is 7.20 times 10 to the negative 10 molar. Once we have our hydrogen ion concentration, we can calculate pH. We use the formula pH is equal to the negative log of the hydrogen ion concentration. We plug in the value for the hydrogen ion concentration, and pH is equal to 9.14. This method is something that you are already familiar with based on our experience with Rice tables. The second method is using the Henderson-Hasselbalch equation. So we have the exact same stimulus, but the first thing that we need to do is calculate pKa. We'll use the formula pKa is equal to the negative log of Ka. We'll plug in our value for Ka, do the calculation, and pKa is equal to 9.31. Once we have the pKa value, we can write the formula for the Henderson-Hasselbalch equation. The next step is to plug in our values from the stimulus. So pH is equal to 9.31, which we just calculated here, plus the log of our conjugate base, which comes from our stimulus here, and the concentration of our weak acid, which comes again from our stimulus. The last thing that we need to do is do the calculation. And once we do the calculation here, pH is equal to 9.14. Note that this matches the answer from the previous slide using the Rice table. Let's do another example. We'll start again with using a Rice table. Determine the pH of the buffer solution that is 0.50 molar NH3 and 0.20 molar NH4Cl. The pKb value is 4.75. We'll start by writing the equation for the strong electrolyte. NH4Cl dissociates into NH4 plus 1 and Cl minus 1. The chemical equation for the equilibrium system is NH3 plus H2O yields NH4 plus 1 and OH minus 1. In the beginning, we have a concentration of 0.50 molar for NH3. The water is a proton donor but is not included in the calculation of the pH. Our concentration of NH4 plus 1 comes from the strong electrolyte, and no hydroxide ions are present. To some degree, the NH3 will react with the water to produce NH4 plus 1 ions, in addition to the concentration from the strong electrolyte, and some amount of hydroxide ions are also formed. The next step is to use the pKb value to find Kb. So pKb is equal to the negative log of the concentration of Kb. We can rearrange this formula where Kb is equal to the antilog of the negative pKb. If we substitute in our value for the pKb, we calculate that Kb is equal to 1.77 times 10 to the negative 5. Once we have this, we can write our equilibrium expression for the weak base, plug in the values from the stimulus, solving for the hydroxide ion concentration. And if we do this calculation, X is equal to the hydroxide ion concentration of 4.42 times 10 to the negative 5. Once we have the hydroxide ion concentration, we can calculate pOH, because pOH is equal to the negative log of the hydroxide ion concentration. When we substitute in our value for the hydroxide ion concentration, we can solve for pOH, and pOH is 2.15. If we subtract this number from 14, we find that our value for pH is 11.85. Let's see this in terms of the Henderson-Hasselbalch equation. To use the Henderson-Hasselbalch equation, we need to start with our pKb value. So we know pKa plus pKb is equal to 14. If we rearrange this formula to pKa is equal to 14 minus pKb, we can find our pKa value. So 14 minus 4.75 will give us a pKa value of 9.25. Once we have our pKa value, we can use it in the Henderson-Hasselbalch equation. So if we plug in our numbers, pH is equal to 9.25 plus the log of our weak base, which comes from the stimulus, and the concentration of conjugate weak acid, which also comes from the stimulus. Solving for pH, we find the pH is 9.14, which again, this answer matches the answer on the previous slide. It's just a different approach to solving for pH. Buffer capacity. Buffer capacity is defined as the amount of strong acid or strong base the buffer can neutralize before the pH begins to change to an appreciable degree. If the concentrations of the weak acid conjugate base ratio is increased while keeping the ratio of these concentrations constant, the pH of the buffer will remain the same, but the capacity to neutralize a larger amount of strong acid or strong base will increase. The relative number of moles of acid and conjugate base is a major factor in determining the pH of the buffer solution. If a buffer solution is diluted, the pH will not change. A buffer solution should control the pH at the desired value. So we need to choose an acid with a Ka close to the intended value of the hydrogen ion concentration. The exact value of the hydrogen ion concentration can be achieved by adjusting the acid conjugate base ratio. The Henderson-Hasselbalch equation can be used to determine the ideal ratio of conjugate base to acid concentration. Conditions needed to buffer a strong acid or strong base. When a buffer has more conjugate acid than base, it has a greater buffer capacity for added base than added acid. When a buffer has more conjugate base than acid, it has a greater buffer capacity for added acid than added base. Buffer capacity and pH range. Buffer capacity is defined as the pH range over which the buffer acts effectively. When the concentrations of weak acid and conjugate base are equal, pH will equal pKa. In future videos, we will be discussing buffer capacity in terms of titration curves like the one seen here. So what did you learn? We talked about factors that influence the pH of a buffer, an overview of the Henderson-Hasselbalch equation, looking at two methods that achieve the same result of determining pH, one using Rice tables and the other method using the Henderson-Hasselbalch equation. We looked at worked examples involving a weak acid and a conjugate base, and another worked example using a weak base and conjugate acid. Finally, we talked about buffer capacity. Need more help? Feel free to contact me. Have a great day.